Well, good afternoon or good morning. Welcome to the first of the Historical Geology Lecture Series. This is going to serve as an introduction to the material that we are going to cover and hopefully get you into the mindset of some of the topics that we are going to talk about. So, as the name implies, historical geology is encompassing the history of Earth processes, essentially trying to tell a narrative or a story, factual story of the history of the Earth, both the surface and snippets of the interior, even, whatever observations we can make, and putting them into the context of time. Now, in terms of time and what we know of it, we construct a lot of things around it. We construct our semesters, we construct our class schedules around all time. We have the construct of many different calendar systems throughout our history, and so on and so forth. So it serves to make sense of our own personal narrative, if you will. But also, when we think about cultural or national context, we have, especially around the time of this recording here in the United States, we have this this need or want to interpret the intentions and motivations of our founding forefathers. If you're viewing this from outside the United States, then insert your own founding forefather. It still serves as a historical reference in helping you to essentially self-govern yourself. Kind of redundant there, but self-governance. And then if you are not disposed to any type of patience or any amount of patience, then you're probably wondering how long I'm going to talk about time itself. It's still all around you. But nonetheless, we're going to put our observations of the geologic processes into the context of time because we want to tell the history of the Earth. Now, in terms of cultural, national, and even genealogical observance or evidence of the past, we look for certain types of human artifacts, if you will, and for the founding forefathers, or if you're anything like me, I suppose, and you're an amateur genealogist, you want to have an idea of what those people in the past were like. Who were they? And that takes a little more than just face value genealogical charts. It takes correspondences, letters, or photos even, perhaps, snippets in time. And that's what we're looking at. And in terms of a human aspect, like anthropology or archaeology, yeah, we view both stone tools and artifacts, architecture, symbols. We try to unravel and interpret what this meant to them and what that meaning then could help us, or how that meaning could help us interpret who these people were. Well, that helps us tell the history of human past, especially civilizations and cultures. But the Earth is no different, really. It's a structured world. We know from physical geology that deposits, specifically in sedimentary rock, they are layered. There's a sequence, there's a madness, or a method to the madness, if you will. Now, you will hear me say this in the other lecture series, and if you take the course, you'll hear me say it in there as well. The Earth writes its autobiography in the rock, minerals, and in the formations that are formed from those materials and the structures as well. If we know the language within which it's writing its history, then we can interpret more correctly the history of the Earth. We just have to read what it's writing, literally and figuratively. But as always, we have to answer a few questions, at least motivational questions. The big why. Why would we want to even study Earth's past? What does it have anything to do with us? We're here. We're now. What does a couple of events in the Precambrian have to do with me today? Well, there are two ways that we can answer this, two kind of broad answers, if you will. One is the obvious or intuitive answer, and that's the economic answer. Obviously, petroleum, gas, and other ore bodies and minerals as such are largely extracted by exploiting our understanding of, first, where those materials form and how they form, and if they're the right materials at all, right? I mean, you have to know the conditions. And secondly, the efficient extraction of those materials. That all has a very large economic impact. And it doesn't matter if you drive a hybrid car, a natural gas car, a nuclear powered car. It doesn't matter if you bike. It doesn't even matter if you walk into school. You still are dependent largely on petroleum for some of your energy needs. Now, when you go on the other aspect of ore bodies, you still are largely dependent on technology. It doesn't matter if you own a mobile phone or a computer, you're still viewing this somehow. And a large part of the world around you is very, very much determined and dictated by the prevalence of those ore bodies, specifically some of the rare earth materials. And that all takes a very, very solid understanding of physical processes that make those materials, and then the physical processes that allow those materials to potentially be extracted, and how you can extract them efficiently, because you don't want to pay more for a material that you have to. So that's fairly big economically. The standard of life that you enjoy is all dictated by an understanding, at least someone's understanding of geology. Secondly, when we look at this figure here, and always when you're looking at a table or a graph or some type of figure, look at the legend and make sure that you know what the colors mean. In this sense, this is a shake map or a hazard map where we have essentially the potential for dangerous earthquakes to occur, and the hotter or warmer colors are higher hazards, if you will. And so we've got some fairly straightforward pockets or complexes of fault systems and earthquake prevalences. We have the San Andreas fault system, right? It stretches all the way up even to the subduction zones of the Pacific Northwest, where we can have very large earthquakes occur throughout this system. Then we have the New Madrid fault system here, just as a couple of examples. So really, okay, what happens if you live in Minnesota? What does it really have to do with anything to me, right? Well, we'll get to that. But first and foremost, understanding what has happened in the past, especially previous deformation events and previous or maybe even buried structures like the New Madrid fault system, that allows you to forecast and predict the types of earthquakes or types of deformation events that might interfere and interact. And I use interact loosely because when earthquakes interact with the surface of the earth, they largely don't, it's a blind process, right? It doesn't really care. It has no mechanism to care what buildings or people it kills or destroys, right? So understanding where these systems are gives you an idea of what to expect if you live there. That's a general thing, right? But when we go a little bit deeper, we have even county-wide hazard maps, right? Level earthquake hazards here in California. That's a pretty much straightforward given. Or even other hazards such as volcanic hazards, right? Well, it takes a whole slew of people, a whole slew of geologists to go out there and look at the previous deposits from previous eruptive events from Mount Rainier, right, in this specific example, and look at the lahars, which are these very nasty volcanic mud flows, cohesive kind of mud flows, these ash flows that stem down these ravines and river systems, these fluvial systems, even all the way down to the city of Tacoma. And that gives us an idea of what might happen if Mount Rainier erupted today. That allows the geologists to communicate to the communities around them and say, hey, look, if you're living here, this is what you can expect if this goes off. At present, it's very difficult to forecast and predict volcanic eruptions as well as predict and forecast earthquakes. So this is what we need to have in place. We need to have a plan, right? And that plan goes on past even volcanic hazards and earthquake hazards. Tied to earthquakes or liquefaction. So when the earth shakes, right, we have this very fine sediment, this unlithified, which means it's not yet rock, right, just loose silts and muds. if that gets shaken, it reacts like a liquid or plastic. So any structures that are built on top of it are obviously not going to be standing upright by the time that event is through. And so we have this liquefaction susceptibility map that allows people who live in this particular area, which is San Francisco area, to understand the hazards of the world that they live on in that particular place. Now, coinciding with some forms of earthquakes, especially submarine earthquakes, we have tsunamis, right? These large plateaus of moving water. Well, we have tsunami inundation emergency maps, and this is a very good map for helping people of Southern California, especially Santa Barbara area, and telling them where to go, right? Obviously, you want to go upland, right? But sometimes, depending on your topography and where you're at in that general geographic area, you need a little more information than just go uphill. You need to have a plan. Where should you go? Because sometimes you might be disconnected from everything else if you just stay in one spot. So you need to have a plan. And this all is because we live on a planet that undergoes unavoidable changes. We talk about bolide impacts, comet impacts. We've got disaster movies galore that talk about them, right? But we have to be able to foresee some of these changes and adapt to them, because as we talk about our lineage, our evolutionary lineage, we will talk about populations adapting to change itself. That's the hallmark of humanity, is that we have the potential to change and adapt to change itself. So the big answer to that question, why, is because your civilization, your standard of life, and your survivability all depends on information, on knowledge. You live in a time frame that is swimming in knowledge. You have access to the internet. It's crazy how much information we have. We have to be able to use that to our benefit, and specifically in terms of these geologic processes that occur. And we didn't even talk about flooding, floodplains, and things like that. We live on this planet by geologic consent alone. Now, that sounds kind of like a soapbox preaching a moment there, but that is fantastically true, and very eerily true when we stop and think about it. So, as we look at the Earth's past, we notice large-scale changes, both from climatic or cataclysmic events and from climate change itself, all the way back during the Ordovician, all the way up. Even in the Precambrian, we'll talk about some events that occur that were probably unavoidable, but life adapts through. So our hallmark is our intelligence. Using our ability to look into the past to see what might happen in the future gives us a very good ability to predict and to plan what we should do in the event that certain cataclysmic processes occur. So hopefully, and I'll step down from the soapbox there, hopefully that answers the question sufficiently. And so when we talk about geology, obviously we're looking more than just at rocks. It's, in a nutshell, obviously the study of Earth and its processes, but when we talk about geology, we split it into two parts. We talk about physical geology, and that's the first or initial course that you take before this one. And that's the study of Earth's material and its varied processes. How do you produce those rocks? How do you produce those minerals? How do you produce structures, etc.? When we look at historical geology, however, we take that information and we put it in the context of time. We talk about and we try to interpret Earth's origin and its evolution. Well, we talk specifically in terms of that about the changes in the distribution of land and seas, the growth and reduction of mountains, the growth and fill-in of basins. And then we obviously talk about the succession of animals and plants through those changes because they have to adapt to different geographic alignments of continents, right, or of oceans, which play a very large role in the climates, or the global climate that those organisms then have to persist through. And all of that takes looking and observing planetary material and structures. Fossils, rocks, minerals, faults, folds, stratigraphic successions of materials, right? We all look at that, and that's the result. That's the result. A rock is the result of processes. The stratigraphic column is a result of time and deposition of material. And so in order for us to tell the history of the Earth, we have to look at the results, that rock, right, or fossil, and then we have to work our way backwards in time to find the causes of that. And to do that and to properly constrain that and interpret that, we have to use a variety of things. First and foremost, we use uniformitarianism or actualism, which is to say the present is the key to the past. What I mean by that is we can go outside and we can view geologic processes happening in real time. There are certain geologic processes that do happen in real time. The bed load or transportation of sediment in a fluvial system, we can see that. We can also construct models, right? Real life models of deposition and formation of sediment on a smaller scale, and use what we see and observe there to translate that to what we see in the rock record, in the rock. And we can get a good idea of how those features formed. Secondly, geology is not a soft science. Many people have this idea that it's rocks for jocks, or jocks for rocks, vice versa, whichever one you want to prescribe to. But really, in order for you to definitively draw a proper narrative or a story or history of the Earth, you really do need to know a lot of different factoids, if you will. You really do need to be familiar with chemistry, physics, math, specifically trigonometry, and biology, especially if you're a paleontologist. You need to be able to draw off of those many different sources of information and other realms of science in order for you to pool that all together and to essentially paint a picture, or tell a story, a factual story of the surface of the Earth or the interior of the Earth at that particular point in time. And that leads us then to talk about what science really is. And this is something we really do need to talk about because even if you're viewing this 8 years on, here back in 2016 and even before, we have these shows on the Discovery Channel and History Channel that really just propagate all these different ideas. They shotgun splatter all these ideas out without really corroborating any of that information into a likely hypothesis that could be tested and that has any type of predictive qualities to it. And so we have this notion then that ideas are facts. We can have these ideas and they're facts. There's no need to elaborate any further than that. There's no need for any predictive qualities or to test our ideas beyond any coincidental evidence that we have. Well, while we are all entitled to our own opinion, we are not entitled to 1,000 million billion gajillion different notions of facts, right? A fact is a fact. It's not equivalent to an idea or an opinion. And that is to say that when we think about science, we largely think about it as a noun, a body of knowledge, right? That makes sense. And that seems pretty good at face value, but that really belittles the nature of how we got that information. All right? You could have a body of knowledge that doesn't say anything as to how you got that knowledge or whether or not that knowledge is actually factually correct. Right? It says absolutely nothing. So first and foremost, when you think about science, don't think about it as a noun per se. Think about it as a verb. You do science. We will do science. It's a way of understanding and deciphering natural phenomena within the universe. Things that we can observe, we try to understand it. And in doing so, we're doing science. That's a verb. Carl Sagan once said that Science is a skeptical way of interrogating the universe. That's really what you should have, a mindset when you go into lab, or even when you're observing things in the field. You really should be skeptical and really draw out your observations in a very detailed manner, such that you can go back and test your ideas. Now, that isn't to say that the noun version of science isn't correct. Obviously, we have this body of knowledge that we call science, right? But there's an interplay between these two. We think about great scientists as inputting their knowledge or their findings, their revelations, if you will, into this body of knowledge, this collective body of knowledge. And that's what happens. It really is what happens. But it's not always a constructive interplay. Think about other scientists, other naturalists that essentially refuted that current body of knowledge. Think about Galileo, Copernicus, right? They added to the body of knowledge, but they didn't really support that current body of knowledge that everybody else had. They actually refuted it. So science is this constructive and even destructive, in terms of the body of knowledge that we have, type of process where we're building a more efficient and more factually correct, continually doing this, sense of the world around us. And when we talk about historical geology, that's no different. We try to observe more and more and more, and we try to build upon our body of knowledge, but also there are things that might refute current ideas or current hypotheses. So when we talk about doing science, you obviously have done it before, and you know the method to the madness. Now, in an earth science sense, it is very, very good and very, very, very worthwhile, obviously, to be able to go in and construct a hypothesis, right? An explanation of your data that has predictive qualities to it, meaning that you should predict what you should observe in later tests, right? And if you don't observe that, then, maybe your hypothesis is wrong, or hypothesis is wrong. Well, there are... and that's not always the way that scientific research, especially in earth sciences, is constructed, but it is something that you will have to get familiar with or get re-familiar with in terms of lab. What you're going to be doing is largely drawing off of your observations. You're going to observe rock, minerals in that rock, textures within that rock, structures within the rock, fossils within the rock. And you're going to use all of that information to interpret what that might mean for the surface of the earth at a given time. Because again, we're historians. We want to be able to tell the history of the earth. And the only way we can do that is by fitting snapshots in time, that rock, right, that you've just interpreted, with other materials and trying to chronologically come up with a history of the earth. And so a good example, real life example, would be looking at the Mediterranean Sea in the northern part of Africa and the southern part of Europe. And what we observe here, this is just going to be general. This is, for you probably don't know this, but if for anybody else, especially specifically familiar with the Messinian crisis, forgive me for a very bad image example. This is not from the Mediterranean and not from that time frame that we're going to talk about. This is just illustrating a faunal turnover where we have a group of organisms here just below that essentially represented open marine fauna in the Mediterranean Sea. And at about 20 million years ago, they're gone. They're no longer present within the Mediterranean Sea. We have endemic fauna within a certain time frame, but then they're gone. And then about 5.5 million years ago, these open marine faunas come back or are prevalent within the deposits that we find. In North Africa and bits and pieces of southern Europe, we find during this time frame incised gorges or incised river valleys where the river has cut down into the rock to try to meet a falling sea level. It's cutting down faster and faster and faster. We also see in the Mediterranean itself plethora, an abundance of salt, thicknesses of salt in kilometers, where later deposition of sediment on top then forces these salts to essentially form salt diapirs or salt domes. Well, on top of the salt, we have a megabreccia, huge clasts, class size that are about the size of cars and even small houses that are right on top of the salt and actually incorporate inclusions of the salt. And then on top of that, we have normal marine sediment as well as normal marine fauna that are within that sediment above. So life goes back to normal. So what happened? Well, it takes us collecting some data, and these are this data is a part of a deep sea drilling project that did drill around all the Mediterranean Ocean, or Mediterranean Sea, pardon me. And it took a lot of observations of those cores, very, very detailed observations. And what and we in the collective sense, the scientific community, I wasn't a part of the research, what they found and what they came up with was their hypothesis that some 20 million years ago, the Mediterranean was a vast seaway, much like what it is today, linked to the Atlantic Ocean through straits or one strait. But that tectonic movement essentially closed that strait, or the connection between the Atlantic Ocean and the Mediterranean Sea. And what occurs from that is a starved basin. The Mediterranean Sea then begins to evaporate. The water from it begins to evaporate, starts forming this starved basin, or a giant salt lake. And when we evaporate that water, we raise the concentration of salt within the water. And if you're familiar with evaporitic deposition or precipitation, that's what we're leading to. When you evaporate more and more water, you're increasing the concentration of the salt within that water, which forces that salt to then precipitate. And there are different salt compositions that precipitate out with different concentrations of salt in the water. So gypsum forms generally first, and we have other types of chlorides like sodium chloride and even potassium chloride that form afterwards. But we have a huge thickness of salt that forms within the Mediterranean Sea. And it's evidence that the Mediterranean essentially evaporated, creating this 3,000 meter bowl or basin where the streams from Europe and from Africa had to cut down to reach that new sea level, which was 3,000 meters below what it once was. And that's what's cutting down and creating these huge gorges and incised valleys that we can see. But about 5.5 million years ago, new tectonic movements essentially reopened the present Strait of Gibraltar in a cataclysmic event that sees the water that's rushing in essentially break the sound barrier. And the force of that motion, the force of that water that's coming through, tears up the salt flats, tears up the tectonic dam, if you will, and incorporates that material into this mega breccia that we can find fairly close to where that cataclysmic event first occurred. Now, the Atlantic Ocean fills in the Mediterranean Sea, and we find in these later open marine deposits, essentially open marine organisms, or organisms that thrive under open marine conditions. And the subsequent deposition of more and more sediment on top of that as time goes on forms this loading, accumulation of weight on top of the salt. And salt is less dense than the surrounding sediment, the overlying sediment. So it pushes up, it domes upwards, much like a lava lamp would do, and forms these salt diapirs and salt domes that we see presently within the Mediterranean Sea. Now, this obviously gives us some avenues for predictive qualities, right? We should be able to see what types of salts are being deposited. We should be able to see within this cataclastic breccia, this flood breccia, if you will. We should be able to see some observations that should be predicted by this hypothesis. And this is what people have been working on for the past, a handful of years, handful of decades, really, since the deep sea observations that were made. But this gives you a good idea of a real working hypothesis in real life. And on a smaller scale, this is what you're going to be trying to do in lab, formulating your observations first, looking at the data that you've collected from that, and then trying to interpret And if your interpretation doesn't really make sense, then go back to your observations. Did I observe something wrong? Is there something else that I might be able to observe in this rock? So on and so forth. So when we get into lecture and I actually give you this, we're actually going to go through and look at a card game. And I'm going to have you draw out your hypotheses from your observations. And a part of that is going to actually be prediction of what the patterns you would expect to see later on. So with that, thank you for your patience, and I will see you for the next lecture in this lecture series. Take care.